All right, question 24, last graphing example we're going to look at here in 4.1. You know the drill. We're told in the following exercise, solve the following system of equations by graphing. 5x plus 2y equals 7 and negative 10x minus 4y equals negative 14. Let's see what happens. So, as we always do, let's begin with the first equation here. So 5x plus 2y equals 7. All right. Again, a couple different things we could do here. We could find the xy intercepts. We could create a table of values. We could put this thing into y equals mx plus b. Really, whatever floats your boat. I think I'm going to just stay consistent and put this into y equals mx plus b. So we'll subtract 5x from both sides. So we subtract 5x from both sides. That disappears, leaves us with 2y on the left is equal to negative 5x plus 7. And then, of course, last thing we're going to do here to get the y all by itself is to divide everything by 2. So that gives us a final equation of y equals negative 5 halves x plus 7 halves. All right, fair enough. Now, here's what I'm going to do, because I want to bring your attention to this little caveat, this little fact that you might start to recognize. Notice that with our equations, notice how there really are two different things happening here. From equation 1 to equation 2, notice how the signs are all flipped, right? Notice the first term is positive, but the first term here is negative. The second term here is positive, the second term here is negative, and then on the other side, the right-hand side, we have a positive constant and a negative constant. So all the signs are flipped. But more than that, what do we notice? Before we go to graph this first equation here, right, so let me put a blue dot here. Let's very quickly take the second equation. Let's put it into y equals mx plus b, and let's see what's happening here. So if we start with, again, negative 10x minus 4y equals negative 14, let's put this into y equals mx plus b, so we'll add 10x to both sides. And that, of course, means that term cancels. We're left with negative 4y is equal to, forgot the x here, now 10x minus 14. And then let's divide everything by negative 4. So we end up now with positive y is equal to, we have a positive divided by a negative, so our sign will be negative, and then 10 over 4. Well, those two factors have something in common, right? They have a 2 in common. So 2 goes into 10 5 times, and 2 goes into 4 twice. And we have our x. We have a negative divided by a negative, which of course is always positive. 14 over 4, well again, that isn't going to simplify into an integer, but they both have what in common? Again, they both have a 2 in common. 2 goes into 14 7 times, and 2 goes into 4 twice. So what do we notice about these two equations? Right? If we look here, we have y equals negative 5 over 2x plus 7 halves. And if we look here, we have the exact same equation. We have y equals negative 5 over 2x plus 7 halves. Well, that means what? That these two equations are really one and the same. It's the exact same equation, just expressed in two different ways. So any ordered pair that satisfies the first equation, any x comma y that you can think of that will make this first equation true, will also make the second equation true. So what does that mean? It means that this system here has an infinite number of solutions. And that might make a little more sense if we visually, again, take a look at what's happening here. So I wanted to bring that to your attention, and now we'll go ahead and graph just like we've been doing for the previous examples. And I'm going to maybe bring some of this over here because it's sort of crowding us. All right, and let's go ahead and go through the process, right? So for the first equation here, our slope is -5/2, so that means we're going to go down 2 units to the right 1, and our y-intercept is going to be 0,7/2, but here's an improper fraction. Let's convert it to a mixed number. 2 goes into 7 how many times? Well, it goes in 3 times with 1 left over, and then we always use the original denominator. So we are going to graph the first equation here. So we start at the origin. The y-intercept is 0,3/2. So 1, 2, 3. There we go. 3/2. All right, or 3.5. And then from there, we're going to go down 5 units and to the right 2. So down 1, 2, 3, 4, 5, to the right 2. 1, 2. So there's the next point, and all we're going to do, well, that was pretty terrible. All right. Oh my goodness, this is not going well. I need to create a little tool that'll help me to graph straight lines here. That'll maybe make things a little easier. All right, but at any rate, so there we have the first line. Let's do the exact same process with the second equation here in pink. But as we've already established, this is the exact same line, right? So we know that the slope here is still going to be -5/2, meaning we're going to go down 5 units to the right 2 units. We still know that the y-intercept, again, is going to be 0,7/2, but converting that to a mixed number as we just did a moment ago, we can see it's 3.5. So if we graph the y-intercept at 3.5 on the y-axis and go down 5 units to the right 2 units, well, you can see what's really happening here. And again, assuming that my lines were okay. It's one line right on top of the other, right? And so when I say that there are an infinite number of solutions, what I'm saying is that there are an infinite number of ordered pairs, right? This ordered pair, and this ordered pair, and this ordered pair, and this one, 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 and this one. There are an infinite number of ordered pairs that make the blue line true, right? That are on that line. And simultaneously, there are the same exact points make the second equation true because it's the same line, just again expressed in 2 different ways. So any ordered pair that's on the blue line is also on the pink line because they're the same line. And so therefore, what we would say is that in this case, there are an infinite, or what we would really say is that there are infinitely many solutions. Right, so that's really sort of the formal way of saying infinitely many solutions. How come? Because these are really the same line, right? The blue and the pink are really the same lines, just expressed in 2 different ways.